Welcome to the Deep Dive. Today, we're going to be tackling a concept that I think is both mind-boggling and endlessly fascinating, and that's infinity.
Yeah.
And it's not just some kind of philosophical abstraction either.
Yeah.
Infinity has really challenged mathematicians for centuries. And today we're going to kind of explore how one person revolutionized our understanding of it.
Yeah, that's right. Georg Cantor, the father of set theory, really kind of turned the mathematical world on its head with his ideas about infinity.
Exactly. And we're working with some excerpts today from a book that's all about infinity and math, with a focus specifically on Cantor's contributions.
Okay.
So what we're going to do is kind of trace the evolution of how people thought about infinity,
Okay.
starting way back with the ancient Greeks and their, head-scratching paradoxes.
Right.
And then fast forward to Cantor's groundbreaking and sometimes controversial theories.
Sounds like a journey. Where do we even begin with something as vast as infinity?
Well, we have to start somewhere. And I guess the ancient Greeks are as good a place as any.
Okay.
They might be known for togas and philosophy, but they were also wrestling with some pretty complex mathematical ideas, too.
Yeah.
Have you ever heard of Zeno's paradox?
Of course it's a classic.
Yeah.
It involves a stone being thrown at a tree, right?
Yep, and here's the kicker.
Yeah.
According to Zeno, the stone can never actually reach the tree.
Now that sounds impossible. What's the logic there?
Well, Zeno argued that before the stone can hit the tree, it first has to travel half the distance.
Okay.
Then it has to travel half of that remaining distance, and then half of that distance,
Right.
and so on, forever.
So you're saying there's an infinite number of ever smaller distances that stone has to cross?
Exactly. And Zeno's point was that you can't complete an infinite number of steps in a finite amount of time.
Okay.
And so he was really using this paradox to try and prove that motion is actually impossible.
Wow.
Just an illusion.
That's quite a leap from a stone and a tree to the very nature of reality.
I know, right? And it was really meant to support a philosopher named Parmenides who believed that the universe was unchanging. So Zeno's thought experiment was basically a logical argument to support that view.
Fascinating stuff. But luckily for anyone who enjoys, moving, another Greek philosopher came along, Aristotle.
Aristotle wasn't buying into the motion is an illusion thing.
Not at all. He saw a flaw in Zeno's logic, and he introduced this really crucial distinction between potential and actual infinity.
Okay, I'm intrigued. Break that down for me.
Okay, so think of a line segment.
Okay.
You can keep dividing it in half over and over again, right?
Right.
But the line itself always remains finite, even though you can theoretically keep dividing it forever.
Right. You're still starting with that same initial line.
Exactly, and that's potential infinity.
Yeah.
The possibility of going on forever, but never quite getting there.
Okay.
Aristotle then argued that the points on a line aren't actually infinite.
Right.
He said that if a line were made up of infinitely many points, each point would have zero length. And therefore, the whole line would have zero length.
That makes sense.
Right.
It's like the difference between a process that could go on forever versus something actually being infinitely big from the start.
You got it. For Aristotle, infinity only existed potentially, like in the case of numbers, which can continuously increase, but never as an actual completed thing.
So for centuries, mathematicians kind of danced around the concept of actual infinity, accepting it as a potential, but never a reality. Until, that is, Georg Cantor enters the scene.
Right, Cantor's work was truly revolutionary.
Yeah.
He dared to tackle actual infinity head-on.
Right.
Which, as you can imagine, shook up the mathematical establishment.
Oh, I bet. So how did Cantor even approach this concept that everyone else was too afraid to touch?
Well, he introduced this brilliant idea called cardinality.
Okay.
And cardinality lets you compare the sizes of infinite sets, which I know sounds crazy at first.
Yeah, size is an infinity. To me, infinity is just, well, infinite. It's like saying one forever is bigger than another forever.
I know, it's counterintuitive.
Yeah.
But that's what's so groundbreaking about Cantor's work.
Okay.
He realized that even with infinite sets, you can still use the idea of one-to-one correspondence.
Okay, remind me what that is again.
Sure. So if you can pair up every element of one set with an element of another set with no leftovers on either side, then those two sets have the same cardinality.
So it's like having a basket of apples and a basket of oranges.
Right.
If you can match up each apple with an orange perfectly, you have the same number of each fruit.
Precisely. Cantor took the same logic and applied it to infinity.
Wow.
One of his most famous examples is proving that there are as many even numbers as there are natural numbers.
Wait, hold on.
Yeah.
That doesn't sound right.
I know.
How could there be as many even numbers as all the whole numbers?
Right.
The even numbers are only half of them.
That's what our intuition tells us, yes.
Yeah.
But our intuition often fails us when dealing with infinity. Cantor showed that you can pair 1 with 2, 2 with 4, 3 with 6, and so on forever. You'll never run out of numbers on either side.
So even though it feels like there should be twice as many natural numbers,
Right.
you can still create a perfect pairing with the even numbers.
Okay, I'm starting to see how infinity can really mess with our usual way of thinking.
It absolutely does.
Hmm.
And to really illustrate this point of how strange infinity can be, there's this thought experiment called Hilbert's Hotel.
Oh, I love a good thought experiment. Tell me about this infinite hotel.
Okay, so imagine a hotel with an infinite number of rooms,
Okay.
and every single room is full.
Okay.
Now a new guest arrives.
Right.
In any normal hotel, you'd be out of luck,
Totally. Sorry, no vacancy.
but not in Hilbert's Hotel.
Okay.
You can accommodate this new guest by simply shifting every current guest down one room.
Okay.
So the person in room 1 moves to room 2, the person in room 2 moves to room 3, and so on.
Okay.
Now room 1 is free for the new arrival.
Okay, that's clever, but what does that tell us about infinity? Well, it shows that with infinity, you can add something new without actually changing the size of the set.
Right.
You still have an infinite number of guests even after you add one more.
So an infinitely full hotel can always make room for one more. This is getting pretty wild.
And we've only scratched the surface. What we've been talking about so far are called countable infinities, things like the natural numbers, even fractions.
Okay.
But are you ready to hear about something even more mind-blowing? Uncountable infinities.
Uncountable infinities. Okay, now you really have my attention. This deep dive is about to get even deeper. But before we go there, I think we need a moment to process all this.
Okay.
Countable infinities are strange enough, but I can't even imagine what uncountable ones are like.
Welcome back to our exploration of the infinite. Before the break, we were about to take a leap into the realm of uncountable infinities.
That's right. My mind is still reeling from these countable infinities and how they kind of defy our everyday logic. But you're telling me there's a whole other level to this?
There is. It all goes back to Georg Cantor and his remarkable insights.
Okay.
All the examples we've discussed so far, natural numbers, even fractions, they all fit into this category of countable infinities.
Okay.
But Cantor discovered something even more mind-boggling, and that's sets that are so vast they can't be counted, even in an infinite sense.
Okay, hold on. How can something be uncountably infinite? Isn't infinity already the ultimate concept of vastness?
That's what makes Cantor's work so revolutionary. He showed that there are different sizes of infinity, and to understand this, we need to talk about one of his most ingenious proofs, called the diagonal argument.
Diagonal argument. Sounds a bit technical. Will my brain be able to handle this?
I promise it's not as scary as it sounds.
Okay.
Imagine you're trying to list out all the decimal numbers between 0 and 1.
Okay.
You know, numbers like 0.123, 0.4567, a 0.891234, and so on.
Okay.
You might think, well, there's an infinite number of decimals, but I can still list them out systematically, right?
Yeah.
But Cantor's diagonal argument shows that you can't.
Really? How so?
No matter how cleverly you try to arrange those decimals, Cantor shows that there will always be at least one decimal number that's missing from your list. It's like there's this hidden number that your system will never capture.
That's wild. So it's not just that there are infinitely many decimals. It's that they're uncountable in a fundamental way.
Exactly. And this has some pretty profound implications. Remember, there's this close connection between decimal numbers and points on a line. Every point on a line can be represented by a unique decimal number.
Right, like how 0.5 represents the point halfway between 0 and 1 on a number line.
Precisely. So what Cantor's diagonal argument really shows is that there are more points on a line segment, even a tiny one, than there are natural numbers.
Wait, so you're saying a little piece of a line contains a bigger infinity than all the whole numbers we can imagine?
That's the mind-blowing truth. And this discovery helped to prove the existence of something called transcendental numbers.
Okay, transcendental numbers, that sounds pretty deep. What are those?
They're a special type of irrational number. Remember, irrational numbers are those decimals that go on forever without repeating, like pi.
Right, pi, 3.14159, and so on. I remember learning about that in school.
Well, pi is a great example of a transcendental number. These numbers can't be expressed as the root of any simple equation. For centuries, mathematicians debated whether they even existed.
Wow.
But Cantor's work with set theory actually helped to prove that transcendental numbers are not only real, but there are an uncountable infinity of them.
Wow, so by exploring infinity, Cantor ended up solving a completely different mathematical mystery, about the types of numbers that exist. That's amazing.
It shows how interconnected different areas of mathematics can be. But Cantor didn't stop there. He went on to develop the concept of ordinal numbers to go even further beyond the infinite.
Okay, I thought we were already dealing with the biggest things imaginable. What are ordinal numbers?
Think of it this way. We have the natural numbers.
Yeah.
1, 2, 3, going on forever, right? That's a countable infinity. But then we have omega, represented by the Greek letter O, and omega comes after all the natural numbers, even though there are infinitely many of them.
So omega is like the end of the natural numbers. But how can an infinite set have an end?
It doesn't exactly have an end in the way we normally think about it. Instead, omega represents the totality of all those natural numbers taken together.
Okay.
It's the first infinite ordinal, but here's the thing, you can keep going.
What?
There's omega plus 1, omega plus 2, and so on, creating a whole new infinite sequence beyond omega.
So it's like we take one concept of forever, reach its limit with omega, and then start counting from there. This is blowing my mind.
That's a great way to think about it, and it doesn't stop there.
Oh, no.
We can keep going, creating larger and larger ordinals, forming a hierarchy of infinities, each one more vast than the last.
A hierarchy of infinities. So it's infinities stacked on top of infinities. It's like those Russian nesting dolls, but with concepts that are already infinitely large to begin with.
Cantor's work really stretched the limits of what we can even imagine, but as you can guess, delving into these realms of infinity leads to some pretty challenging paradoxes.
Paradoxes? Oh, no. Does this mean Cantor's whole theory falls apart?
Not necessarily, but it does show how tricky infinity can be. These paradoxes actually reveal some of the inherent challenges of dealing with concepts that are so far beyond our everyday experience.
Well, I'm all ears. Tell me about these paradoxes. What kind of problems arise when you start playing with these different levels of infinity? All right, we're back. And I'm ready to kind of delve into these paradoxes that you mentioned.
Okay.
Exploring infinity is clearly a wild ride, but where exactly do these contradictions kind of pop up?
Well, one of the most famous paradoxes that emerged from Cantor's work is called the set of all sets paradox.
Okay, the set of all sets. That already sounds like we're venturing into dangerous territory.
Right.
What's the paradox?
So imagine you could create a set that contains all sets.
Okay.
It seems straightforward enough, right? But here's where things get a little tricky. A set can either contain itself as a member or not.
Okay.
So let's consider this special kind of set, a set that contains all the sets that are not members of themselves.
Okay, I'm following so far. So this special set only includes sets that don't contain themselves.
Right.
That's the problem with that.
Yeah, ask yourself this. Does this special set contain itself? If it does, then it shouldn't be in the set because the set is defined as containing only sets that don't contain themselves.
Right.
But if it doesn't contain itself, then it should be in the set because it fits the definition.
Whoa, that's a real mind bender. So trying to define a set that contains all sets leads to this unavoidable contradiction.
Exactly. It really highlights the limits of our intuition when dealing with concepts as vast as infinity.
Yeah.
And this wasn't the only paradox that arose. Bertrand Russell, another brilliant mathematician, he discovered a very similar paradox.
Well, I've heard of Russell's paradox. It's the one about the barber, right?
Right. Close. That's a popular illustration of the paradox, but the actual version involves sets.
Okay.
Russell asked whether the set of all sets that don't contain themselves contains itself.
Right.
And again, you run into that same contradiction, a set that both must and cannot contain itself.
So these paradoxes basically revealed some cracks in the foundation of set theory. Does this mean Cantor's work was wrong?
Not at all. His insights about different sizes of infinity and the hierarchy of infinities remain fundamental to mathematics.
Okay.
But these paradoxes did force mathematicians to rethink the very foundations of set theory, to try to figure out how to avoid these contradictions.
I can imagine that sent shockwaves through the mathematical world. So how did they address these fundamental problems?
Well, these paradoxes led to the development of something called axiomatic set theory.
Okay.
Instead of relying on intuitive ideas about sets, which clearly led to problems.
Right.
Axiomatic set theory starts with a set of very precise rules, or axioms, for defining sets.
So they basically created a stricter rule book for playing the set theory game to prevent those logical fouls.
Exactly. One of the most common axiomatic systems is called Zermelo-Fraenkel set theory, or ZF for short. And ZF lays down these very specific rules for how sets can be constructed and avoids those paradoxical situations that we talked about.
That makes sense. It's like building a house on a solid foundation. So despite those initial paradoxes, Cantor's work ultimately led to a more rigorous and well-defined understanding of sets.
Absolutely. And his work didn't just impact set theory, it revolutionized how we think about infinity across many areas of mathematics.
Yeah, it's amazing how exploring something as abstract as infinity can have such concrete and lasting effects on a field like mathematics.
Yeah.
I'm curious, though, how was Cantor's work received by his fellow mathematicians at the time? Was everyone on board with these radical ideas?
Well, as you can imagine, not everyone was thrilled about having their fundamental assumptions about mathematics challenged. There was a lot of resistance, especially from mathematicians who believed that mathematics should only deal with finite, concrete things.
So even within the world of mathematics, there were philosophical debates about whether something like actual infinity had a legitimate place in the field.
There were, and those debates kind of continue to this day.
Wow.
Some mathematicians, like Leopold Kronecker, were very strong opponents of Cantor's ideas. Kronecker famously said, "God created the integers, all else is the work of man," implying that anything beyond the basic whole numbers was straying too far from true mathematics.
So it wasn't just about mathematical proofs and theorems. It
Right.
was really about the very nature of mathematics itself.
Exactly.
That's fascinating. So where do things stand today? Is Cantor's work now widely accepted?
Cantor's work is now considered absolutely fundamental to modern mathematics.
Okay.
His ideas about set theory and different sizes of infinity are woven into the fabric of many mathematical fields. However, the philosophical debates about the meaning and validity of different set theories, those continue.
Right.
Some mathematicians view math as this very formal system, while others see it as a way to uncover these deeper truths about reality.
It's incredible to think that something as seemingly abstract as infinity can spark such profound questions about the nature of mathematics and even the nature of reality itself.
It really is, and it all goes back to Cantor's courage to question assumptions and explore the unknown, even when it led to paradoxes and pushback from his peers. His work is really a testament to the power of human curiosity and the endless potential of the human mind to grapple with the most challenging concepts.
This has been an incredible deep dive. I'm leaving with a whole new perspective on infinity and its implications for mathematics. But I have to ask, if there are all these different sizes of infinity, is there a biggest possible infinity?
That's a question that continues to fascinate and challenge mathematicians and philosophers, the concept of an absolute infinity, an infinity that encompasses all others.
Right?
It's something we can speculate about, but it remains a mystery.
Well, I guess that's a fitting end to our exploration of infinity then. A reminder that there are still mysteries to be explored and maybe some things that will always remain beyond our grasp.
Exactly, and that's the beauty of it. The pursuit of knowledge is an ongoing journey, and the concept of infinity is a reminder that there will always be new frontiers to discover.
Well said. And on that note, we'll wrap up our deep dive into infinity. To all our listeners out there, keep questioning, keep exploring, and keep that sense of wonder alive.